Okay, so hi everyone, welcome back. What we're going to be doing today is starting a new lecture, and the topic is heat and the first law of thermodynamics. So the content from this lecture is coming from chapter 19, sections 1 through 2, and then also sections 6 through 9. We also are taking a little bit from chapter 18 of the textbook, sections 1 through 2. So do read those sections in addition to watching this lecture. And as we go through this video, I just want to remind you that you should be taking notes just like you would be in a face-to-face class. So have a notebook by your side, take notes as you follow along with the lecture, and especially when we get to things like derivations and example problems, it's really going to be beneficial for you if you follow along in your notebook. So just want to give you a heads up about that. So with that said, the first topic is the kinetic theory of gases. All right, so let's talk about the kinetic theory of gases. So this was a theory that was originally developed back in the mid-1800s, and it describes a gas as a collection of a really huge number of particles that are in constant and random motion. Now, the particles are so small that we can't see them directly with our eyes, so we say they're microscopic. If you look at the picture at the bottom of the slide, we have a box of gas. Some number of particles are inside that box. And if you look at their velocity vectors, you'll see that they're not pointing in any particular direction. So, in other words, the particles are just moving in completely random directions. If we were to watch the motion of these particles play out, you would see that they would be constantly bumping into one another, they would be bumping into the walls of the container, and overall the motion would look very complicated and chaotic. One kind of amazing thing about the kinetic theory is that it was developed way before atoms were actually discovered. So at the time, in the mid-1800s, there was a debate among physicists as to whether atoms actually existed. So the question was, could you take some amount of matter, let's say hydrogen gas, for example, and break it down into smaller and smaller parts? Would you eventually get to a point where you can't break it down any further? Would you get to sort of a smallest component of matter? So now we know that yes, there's such thing as a hydrogen atom, and that's the smallest component of hydrogen gas. But at the time, that was very much up for debate. So people took that idea that yes, matter was made out of some kind of smallest part, and they took that and ran with it and developed the kinetic theory. So again, if we think about the motion of these tiny little particles, it's very complicated and chaotic. But another amazing thing about the kinetic theory is if you start with that description of this really complex and chaotic motion of a huge number of particles, what you can get out of it is a really simple description of the gas on the large scale. So in other words, we can understand things like the pressure of the gas and the temperature of the gas by thinking of the gas as being made up of these tiny little particles. Okay, so what we're going to do next is a derivation. It is a bit of a long derivation, but at the end, there's a really important result that we get to. So let's start by saying that we're going to be looking at a box of gas. So we have let's consider a box of gas with dimensions L by L by L, so it's a cube-shaped box. And in the box we have N gas particles. So N is just the number of particles in the box. Okay, so let's draw the box. It's shaped like a cube, something like this, and then the length on each side of that cube is L. And in that box, we have, again, N particles. So N can be whatever you want. It doesn't really matter for the purposes of what we're doing here. Okay, so the next thing I'm going to do is we're going to look at a collision of one particle with one wall of the container. with one wall of the box. So what does this look like? Well, let's say the wall is right here. So we have a particle, its mass we'll say is m, and it has a velocity before it hits the wall, and we know that it's going to be moving towards the wall like this. So let's call this v initial velocity. And then it bounces off the wall. So after it bounces off the wall, it has some final velocity, call it vf. And so let's actually draw some coordinates. Let's call this the y-axis. And then let's call this the x-axis. And this will help us keep track of the motion. Okay, so the next thing we'll do is we'll break v initial and v final down into components. And so we have the x and y components shown right there. And one thing that we're assuming here about this collision, by the way, is that the collision is elastic. And what that means is the same amount of kinetic energy in this molecule before and after it hits the wall. In other words, the same speed before and after collision. So even though it's changed direction, it has to have the same speed. That's the idea. Okay, well, let's look at the y component of velocity. Let's call this Vy. Okay? The wall that it hits doesn't actually exert a force in the y direction. It doesn't push the molecule in the y direction. So Vy should stay the same after the collision. So it's the same y component of velocity before and after the collision. As far as the x component of velocity, that is going to change because initially the x component is negative because we're moving in the negative x direction. And then afterwards it's positive. But other than that, it's the same because we have to be moving at the same speed before and after collision. So what we see is the x velocity just flips a sign. That's how we describe the molecule bouncing off of the wall. Okay, so the next thing we'll want to get at is the force. Okay, so now we're going to consider the force, the average force, okay, on the wall due to one of these collisions, or let's say due to one particle. So the idea is when the particle crashes into the wall, it exerts a force on that wall, and we can calculate that force. So we're going to write this as F with a bar on top. So the bar on top just means we're talking about an average. So that's going to be the notation. And how can we calculate force? Well, you know, one way would to use Newton's second law, F equals ma. But there's actually another form of Newton's second law that I hope you remember from back in Physics 45. We can write it as F equals ma, or just as well, we can write it as delta P over delta T. So the change in momentum over the time is another way of thinking about force. And in particular, we can look at our picture and we can see that the momentum is only really changing in the x direction, so we can just focus on that. Okay, so the next thing is, what is the change in momentum? What is the change in momentum of our particle, delta P, and how do we write that out? Well, that's going to be the final momentum in the x direction minus the initial momentum in the x direction. And we can write down what that is straight from our picture. So we have, remember, momentum is mass times velocity. So the final momentum, I should say, is mass times plus Vx, because again, that's our final momentum over here. And our initial momentum is mass times negative Vx. So anyway, this is how we write the change in momentum that the particle undergoes because it crashes into the wall. So these two negative signs cancel. And overall, we just get 2 times m vx. That's how we express the change in momentum. Okay, the next thing I want you to think about is speed. The definition of speed, how fast this particle that we're looking at is moving, is the distance it moves divided by the time. So if we think about the speed and just focus on the x direction, well, how far does it actually move between collisions with the wall? So I want you to just look back at this initial picture of the box. So a particle comes in, it hits a wall over here, and then it has to travel all the way across the box, and then it has to come back before it hits that same wall again. So in other words, it has to travel twice the length of the box before it hits that same wall again. So we'll say that the distance will be 2L, and the time we'll just call it delta t. Okay, so 2L again is the distance between collisions with that same wall of the container. Okay? So delta t, if we solve for that, just to rearrange what we wrote down, is 2L divided by Vx. Okay? And therefore the force on the wall that we were alluding to earlier, remember, is delta px over delta t. Well, delta px, we just said, is 2 times m Vx. And delta t is 2 times L divided by Vx. So overall what we have is m times Vx squared on top. Factors of 2 cancel. And we have L on the bottom. So this is a really important place to just kind of take stock of where we are. What we just calculated is the average force on the wall of the container due to one of these particles. Okay, well, what happens then if I look at all of the particles together? In other words, what if I want to know the force on one wall due to all particles? Okay, not just one. Well, in that case, what I would have to do, let's say this is F total. In that case, I would have to add up all of these different force terms. Each one of them looks like m times Vx squared divided by L, but I have to add them all up for all the different particles. Okay, so we have a big sum coming up. By the way, m divided by L is going to appear in every single term in the sum, so I'm going to pull that out. But then I have v1x squared plus v2x squared plus, and this might be a huge sum, so let's just say dot, dot, dot. The last one is vnx squared. That's how we sum over all the different particles. Okay, and if we do that, we get the average force on that wall due to all the particles. Okay, so we're going to do a little bit more work. First, let's think about what it means to talk about the average of some quantity. Let's say the average of Vx squared. Well, whenever we calculate an average, we take basically the sum of all of the different values. So we have v1x squared plus v2x squared and so on until we get to the last one. But then we also have to divide by the number of particles. That's how we would calculate an average. And since we're calculating an average, let's put a little bar above that thing, just to, again, indicate we're calculating an average. Okay, what about the definition of speed? Let's bring that into the picture. Remember, if I have x, y, and z velocity, then I can calculate the speed. Basically, the speed squared is vx squared plus vy squared plus vz squared. That's how I calculate speed based on x, y, and z components. And this is also true if we're talking about averages. So I can put a little bar above that to indicate we're talking about averages. Okay. Next fact that I'm going to write down is that there is no preferred direction for the motion. So in other words, if I look at the average velocity of the particles in the x direction, or in the y direction, or in the z direction, I shouldn't be getting anything different because there's no preferred direction. So in other words, what we can say is the average of Vx squared is the same as the average of Vy squared is the same as the average of Vz squared. Those are all the same thing. Which means that if we go back to our definition of speed, okay, average speed squared, well, the three terms I'm adding together, Vx squared, Vy squared, and Vz squared, they're all the same. So I could just write this, if I wanted to, as 3 times Vx squared. Okay? So therefore, let's go back to our force expression up here. What is that term in brackets? Well, that term in brackets again is, v1x squared plus v2x squared plus ... We know we can write that as n times the average of Vx squared. That's coming from the definition of the average, right? If I just multiply both sides by n, I'll get this result. Okay, but also what I can do with that is I can use this result down here, which says the average of Vx squared is a third of the average of the speed. In other words, here, I have n times a third of the average of the speed squared. Okay? And so we can write the force in a much more simple way. Okay, the average force from all of the different particles hitting that wall is going to be m divided by L times n times a third times the average speed squared. Okay. So we're going to keep going with this. Let's write down a formula for the area of the wall. So remember, the shape of the box is a cube with length L on every side. So the wall is going to be shaped like a square, and the area is going to be L squared. Let's also remember the definition of pressure. So pressure is defined as force per unit area. Why don't we apply that definition to the wall of the container that we're talking about? So the force of all those different particles hitting the wall, we just said, is m over L times n times a third times the average speed. That's not coming out so well. The average speed squared, okay? And then we're dividing that by the area, which is L squared. So for the pressure of the gas, just to kind of write that in a more straightforward way, we have a factor of a third out front. Overall, we have L cubed in the denominator. And then we have N, which is the number of particles. Then we have M, the mass, and then V average squared. So I'm going to write this in a slightly different way. And hopefully when I write it in this slightly different way, you can see what I'm getting at. If I pull out a factor of 2 to the front, so we have 2/3 here, and then 1 over L cubed over here, and then N over there, I have to put a factor of a half to compensate for the factor of 2 that I added. And then we'll have a half times MV average squared. So that should be looking really familiar, what I put in the parentheses here, because this is the average kinetic energy of the gas molecules. And also, this L cubed on the bottom is the volume of the box. So therefore, I can write the pressure in the following way. I've got 2/3, and then I have N on top. I have V on the bottom, that's the volume. And then the 1/2 mv squared is the average kinetic energy. So I'll write that as K with the little bar on top. The next thing I want to do is introduce the ideal gas law, which there are different ways we can write it, but I'm going to use the form PV equals N times Boltzmann's constant. So that's a different K, so I'll write it as KB times the temperature. And okay, let's rearrange the ideal gas law. If I want to solve for N divided by V, okay, that would be equal to P. N divided by V would be P divided by, actually, sorry, let's scratch that. Let's write this over here as K bar is equal to 3/2. So in other words, we're solving for the kinetic energy, which is 3/2 times PV divided by N. Okay, that's what I wanted to say. And then if we use the ideal gas law, what's PV divided by N? Well, I just have to divide by N on both sides. That's Boltzmann's constant times T. Okay? So in other words, the average kinetic energy is 3/2 times Boltzmann's constant times T. And there's the result we've been getting at this whole time. Okay? Really, really important result. It says that the average kinetic energy of the gas molecules is directly related to the temperature. So we have a connection between kinetic energy of molecules or of particles and the temperature. That's what this derivation is all about. Okay, so what we just did, to summarize, is we came up with a microscopic interpretation of what temperature means. In other words, we established that there's a connection between temperature and how the atoms and molecules that make up something are randomly moving around, okay? So at least for an ideal gas, we've proved that the average kinetic energy per gas molecule, that's K bar over here, is equal to 3/2 times Boltzmann's constant times the absolute temperature of the gas. So by the way, in order for this to work, we have to be talking about absolute temperature in the Kelvin scale. And even though we only proved this result for an ideal gas, it's actually generally true, okay, that the average kinetic energy of the molecules that make up a system is directly proportional to temperature. So that's really what temperature means in some sense, okay? When you say an object has a certain temperature, you're making a statement about the kinetic energy of the molecules that make up that object. You're making a statement about the random motions of the molecules that make up an object and how fast they're just randomly moving around. Okay? So I'm kind of repeating myself a little bit here, but it bears repeating that we have an important connection between the microscopic world, where we have this random motion of huge numbers of particles, and the macroscopic world, where we can measure something like temperature. And so I just want to show you a video, which is a simulation of an ideal gas. I think I've shown you this before, but it's good to go back to it. So what we have is a huge number of particles constantly bumping into each other, constantly bumping into the walls of the container. And again, the motion is very chaotic, but we can say that on average, those particles have some kinetic energy. So we can calculate some average kinetic energy for those particles. And that average kinetic energy is always directly proportional to the temperature of that gas. And in fact, it doesn't have to be just gases we're talking about. This really generally holds true. That temperature is telling you something about those random motions of those particles. So by the way, if you want to take a look at this animation, I took it straight from Wikipedia, and there's the link if you want to take a look at that. Okay, so the next thing we're going to do is take the result that we derived and go a little bit further with it. In particular, we want to go from a statement of kinetic energy, that's what we have on the left side of the equation here, to a statement about speed. How fast are these gas molecules actually moving? So we know that kinetic energy is given by 1/2 mv squared. So in the equation we derived, I'm going to just replace kinetic energy with 1/2 mv squared. And since we're dealing with averages, right, K with a bar on top means we're talking about the average kinetic energy. V squared also is an average. Okay, so there's a little bar above that as well. And what we want to do is solve for the speed. We want V on its own, not with any sort of square on top of it. So what we're going to do is take the square root. So let's be really, really clear about what we're doing here. We're going to take the square root of the average of V squared. Okay, that's kind of a lot to say, but the name of this thing is VRMS. So the root mean square is a type of average. What you do is you square all of the values, you find the mean of that, and then you take the square root of that. So really that is what this is saying, right? Because we start by squaring all the values. We're talking about speed squared. And then the bar on top says we're taking the average of that, or the mean of that. And then when we square root, that's the final step. So when you do this process, it's called the root mean square, and that's what we're calculating here, okay? So first of all, I can just cancel out factors of 2 on each side. I'd have to divide by m, so it puts it on the bottom over here. And then again, I'd have to square root. So VRMS is the square root of 3 times Boltzmann's constant times temperature divided by m. This gives you the RMS speed of the molecules in an ideal gas. So now what we have is a relationship between temperature and how fast the molecules are actually moving in terms of speed. Now, again, it's really worth saying that this is only a sort of average or typical speed. In reality, there's going to be a whole range of speeds, but this would be the average. Okay, so let's do an example where we actually use this result. What is the RMS speed of N2 molecules in the air at room temperature? So that's 20 degrees Celsius. And then what is the RMS speed of O2 molecules in the air at room temperature? So we do need to know the mass. So for N2 molecules, the mass is 28 AMU. For O2 molecules, the mass is 32 AMU. And just remember that an AMU is 1.66 times 10 to the minus 27 kilograms. So let's do this calculation, or these two calculations, and see what we're getting for the speed of nitrogen and oxygen molecules in the air. Okay, we'll start with this. Room temperature is 20 degrees Celsius, but we're going to want that in Kelvin, because in order to use the results that we derived, remember we have to be using absolute temperatures in the Kelvin scale. So I'll take 20 plus 273, that's how I convert to Kelvin, which gives us 293 Kelvin. So let's start with the nitrogen N2 molecules. Well, VRMS is given by the square root of 3 times Boltzmann's constant times temperature divided by the mass. Okay, so we have 3 times Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin. And the temperature we just said is 293 Kelvin. And then we divide that by the mass. So N2 molecules have a mass of 28 atomic mass units, AMU, but each atomic mass unit is 1.66, 10 to the minus 27 kilograms. So for this calculation, we want everything in SI units. And actually, let's just do a quick side note about the units. Kelvin, you see, will cancel out here, and we're left with the square root of joules divided by kilograms when we look at the units. But joules are equivalent to kilograms meters squared per second squared. That's how you break it down into the base SI units. And so we're dividing that by kilograms and then taking the square root. And then we'll cancel out kilograms. So it's the square root of meters squared per second squared, which is just meters per second. That's what we expect a speed to come out in. I just want to show you that it does work out that way. And if you do the calculation, you're going to get 510 meters per second. Okay. Now let's look at the O2 molecules. And the only difference here is the mass, okay, because we're assuming the same temperature, room temperature. So VRMS in this case is going to be the square root of 3 times 1.38, 10 to the minus 23. I'm going to leave the units off this time. You've seen how they work out. The temperature is 293, but this time the mass is a little bit greater. 32 atomic mass units for O2 molecules times 1.66, 10 to the minus 27. And again, we've seen that this will work out in meters per second. Works out to 480. Okay, so here's the thing. The N2 molecules and the O2 molecules have the same kinetic energy on average, but since the O2 molecules are more massive, they move a little slower. Okay, so if you have a gas with different types of molecules and they're all at the same temperature, you're going to find that the more massive molecules move slower. Because if everything has the same kinetic energy on average, then the things with more mass will end up moving slower speeds. Okay, so I'd like you to try this one out. Let's say we have a metal vessel containing 1.35 mole of helium gas, and it has a volume of 0.0175 meters cubed. The RMS speed of the atoms in the vessel is 725 meters per second. The helium atoms have a mass of 4 AMU, and remember that an AMU is equal to 1.66 10 to the minus 27 kilograms. So 2 questions here. What is the absolute temperature of the gas in Kelvin? And what is the absolute pressure of the gas in pascals? So see if you can work this out, and pause the video at this point, see if you can get the answer, and then come back to it and compare with me. Okay, so we're going to start with VRMS is equal to the square root of 3 times Boltzmann's constant times temperature divided by mass. Now, in this problem, we're interested in finding the temperature. We know the RMS speed, so we'll square both sides. So to get rid of the square root. And the next thing we'll do is we'll multiply by the mass on both sides and then divide by 3 kb on both sides. So we're going to get T is equal to m times VRMS squared. And then we'll divide by 3 times kb. Okay? That's going to give us the temperature that we're looking for. So the mass of helium molecules, or helium atoms I should say, is 4 times 1.66, 10 to the minus 27. Units here are kilograms. RMS speed that we're given is 725 meters per second. And we'll square that as well. Then we'll divide by 3 times Boltzmann's constant, which is 1.38, 10 to the minus 23. Joules per Kelvin. Okay, so if you do this calculation, you're going to get 84.303 Kelvin, but we'd want to round that to a nice 84.3 to keep the correct number of sig figs, Kelvin. So that's a very low temperature, by the way. Okay, the next thing we'll do is we'll find the pressure. And the way we can do that is by using the ideal gas law. Okay, so first, we're going to say that PV equals NKT, Boltzmann's constant is K. And if we want to solve for the pressure, that would just be N times Boltzmann's constant times the temperature divided by the volume. And in this case, we know everything that we need to plug in here. We know the temperature, we know the volume. We do know the amount of gas, we know N, but we have to convert it from moles to numbers of particles, because when we use this form of the ideal gas law, capital N represents the number of particles. So here we have 1.35 mole. In every 1 mole, we know that's the same as 6.022 10 to the 23 particles. So what we're dealing with here is 8.1297 10 to the 23 particles, but just keep in mind we're going to round it off to 3 sig figs. So therefore, the pressure that we're looking for is 8.1297 10 to the 23. Boltzmann's constant is 1.38 10 to the minus 23 joules per Kelvin. The temperature, 84.303 Kelvin, divided by the volume. So we have 0.0175 cubic meters. And also notice that units of Kelvin just cancel like this. You do this calculation, you should be getting 5.4045 10 to the 4th. And we'll keep 3 sig figs. What are the units we're left with? We have joules divided by cubic meters. In the last lecture, I showed you that joules per cubic meter is the same as pascals. So the result is 5.40 10 to the 4 pascals. That's the pressure of the gas. Okay, so the last thing that I want to talk about in the kinetic theory of gases is the Maxwell-Boltzmann distribution. So we have a way of calculating VRMS, which you should think of as sort of an average or typical speed that particles in the gas have. But in reality, you should also have in the back of your mind the fact that not every single particle has that speed, right? There's a range of speeds, and VRMS is just the most common speed that you're going to find. So if we want to be a little bit more detailed in our description, we can use the Maxwell-Boltzmann distribution. And what this distribution does is it tells you the probability that a random particle that you pick out of the gas will have a certain speed. So it's best understood by looking at this graph. On the vertical axis, we have probability. And on the horizontal axis, we have velocity. And so we have a curve which goes up and then it peaks and then goes back down. So what this is saying is, let's say I'm over here, way on the left side of the curve. And by the way, since we're on the left side, this means the velocities that we're thinking about are very small. So the fact that when velocity is small, the probability is also small, that's telling you that it's not very common for particles to have velocities over here. But as we work our way up, then it starts to peak. The velocities in this region, where the graph is peaking, are very probable. So that this is, in other words, the most typical speed that you're going to find. But then as you go to even higher speeds, it starts to fall off again, meaning really, really high speeds are less common. Okay? That's the idea behind the Maxwell-Boltzmann distribution. And it turns out for every temperature, there's a different curve. So we have this red curve for the temperature T1, and we have this green curve for the temperature T2, and T2 is a higher temperature. It makes sense because notice how, on average, things are moving faster in this curve compared to this curve. So we know we're dealing with a higher temperature. And in general, as you increase the temperature, the distribution of speeds that you get becomes wider. So the green curve is also a little bit wider than the red curve. And the peak is at higher speeds, meaning typically things are moving faster at this temperature than at that temperature. This is not really something we're going to take a look in depth at. We're not going to look at the equations that describe these curves, but I just wanted to sort of bring it to your attention that there's a lot further we can go in the kinetic theory of gases. And if you take upper division physics, if you transfer to university, you might learn a little bit about the Maxwell-Boltzmann distribution. All right, so next we're going to take a look at the first law of thermodynamics, and specifically how we can apply the first law to an ideal gas. So let's just do a quick review of what the first law says. The first law of thermodynamics is essentially a statement that energy is conserved. So the way we typically set this up is we define some sort of system. These are just the things you're keeping track of. And everything else is the environment. So anything outside of your system is what we call the environment. And of course, the system and the environment together make up everything that there is. So that's what we might call the universe. So the equation says, and let's focus on the left-hand side for now, delta K plus delta U plus delta E internal, and those are all deltas. So those are referring to some kind of change. If we think about all of these terms together, that's the change in the total energy of your system. Now, what are different ways your system can have energy? Well, it can have kinetic energy, it can have potential energy, and it can have internal energy, right? So the change in all those different forms of energy is what we see on the left-hand side. On the right-hand side, what we have is work, the work done by external forces, plus heat. So these are just different ways that energy can flow in or out of the system, right? You can have energy flowing in or out of the system through work or through heat. So the overall picture that you should have is that you have a system and it has some amount of energy. If there's energy going into your system, okay, and that can be in the form of work or heat, then the energy of that system has to increase. Okay, if there's energy flowing out of your system, then the energy of your system is going to decrease. All of that is contained in this equation. All right, so next, let's see how we can apply the first law of thermodynamics to an ideal gas. So our system is going to include some collection of gas molecules, but nothing else. So our system is just the gas itself. Everything else is going to be the environment. Now, what you should be imagining is the gas is in some kind of container, and that container is not moving in any noticeable way, right? So maybe it's a container of gas just resting on the table, let's say. And because it has no macroscopic motion, what we would say is delta K is equal to 0, so no kinetic energy changes, and delta U is equal to 0, no potential energy changes either. But you may be thinking, well, the gas molecules themselves have some energy because they're moving around, and that's true, but that's what we call internal energy, and we're going to account for that energy with internal energy. Okay, the next thing is we need to talk about work. So the variable W refers to work, and when it comes to gases, what we typically do is we use the W variable to refer to the work done by the gas, by the system, on its environment. So in the conservation of energy equation that we just outlined before, the W term means just the opposite. It means the work that the environment is doing on the system. So by Newton's third law, we can relate those two things. The work done by the system on the environment is equal to the negative of the work done on the system by the environment. I'm going to flesh that out in a little bit more detail in a second in case that's confusing, but the net result of that is we can get this equation out of the first law of thermodynamics, which says that Q is equal to W plus delta E internal, where again W is the work done by the gas. So what is this saying? Heat transferred to the gas from the environment, and that's Q, is equal to W, the work done by the gas on its environment, plus delta E internal, that would be the change in internal energy of the gas. So to show you how we got that result, let's let's write down the first law of thermodynamics. Delta K plus delta U plus delta E internal equals work external plus Q. All right, so we already said that we can cancel out delta K and delta U because there's no macroscopic motion in this system. And also, let's take a closer look at the work. What does work external mean? Well, this is the work done by the environment. So let's call that E on the system. That's the meaning of W external. We'll call the system S. So what does Newton's third law say? It says any force has an equal and opposite reaction force to it. So we can write this in equation form as any force that the system exerts on the environment is equal to the negative of the force that the environment exerts on the system. That's really how we say they're equal and opposite forces, okay? And what if we take that equation and we just sort of integrate on both sides? Let's say F system environment dot some kind of displacement dr equals minus, we'll integrate the other side as well, force that environment exerts on system dot with some kind of displacement dr. So in other words, I'm just integrating both sides of Newton's third law. But we should recognize that, yeah, when we take force and we integrate it like this, we're talking about work. That's really the definition. So this says the work that the system does on the environment is minus the work that the environment does on the system. And since we want the work to mean the work done by the gas, basically that means we're putting a negative sign in the equation, okay? That's where the negative sign comes in. So here we have delta E internal equals minus W now, plus Q. And we can rearrange that to say Q is equal to W plus delta E internal. So that's where the result comes from. Okay, so now let's take a closer look at the result we just derived. This is the first law of thermodynamics applied to an ideal gas. It says that Q is equal to W plus delta E internal. We really want to understand this equation. We want to understand all the variables in the equation and what they mean, and also how they relate to each other. So Q is heat. And when heat flows to a gas, Q can be positive or negative depending on the situation. So if Q is positive, that means energy is flowing into the gas. If Q is negative, that means energy is flowing out of the gas. So when that happens, that energy can go into one of two places. It can go into work or into changing the internal energy of the gas. So in other words, if you have heat flowing into your gas, that can cause the gas to do some work, or it can cause the internal energy of the gas to change, or maybe both. These are just the two places the heat can go. So when we talk about work, for a gas, really this means that the volume of the gas is changing. We're going to show this later, but for now, let's just say work done by a gas means the volume is changing in some way. And work can be positive or negative. When work is positive, that means the gas is expanding. When the work is negative, that means the gas is contracting into a smaller volume. Okay, and then we have internal energy change, delta E internal. Whenever we have internal energy changing for a gas, that means the temperature is changing. And internal energy increasing, delta E internal being greater than 0, in other words, that means the temperature is increasing. And on the other hand, if your internal energy is decreasing, you're losing internal energy, that means the temperature is decreasing. Okay? So that's what all the variables in this equation mean. All right, so before we dive any deeper into the equations, let's go over some terminology and some concepts that we're going to need to really have clear before we start doing any calculations. And the first thing is internal equilibrium. So what this means is that you have a system where every part of the system is in thermal equilibrium with every other part. And if you remember, the meaning of thermal equilibrium is that things reach the same temperature. So we're talking here about a system where everything is in equilibrium with everything else, and everything just has the same uniform temperature throughout. It's important to actually keep this in mind because it's possible for a system to not be in internal equilibrium. For instance, if the system undergoes a really sudden change, it can actually be thrown out of equilibrium. For instance, if you have a room full of gas, if I light a match at one end of the room, suddenly that side of the room has a bigger temperature than the other side. So that's not what we're talking about when we're talking about internal equilibrium. We're talking about everything having the same uniform temperature throughout. Okay, and that leads us to the idea of a quasi-static process, okay? So a quasi-static process is a way of changing the system very, very slowly. So you carry out whatever change that you're doing in tiny, tiny infinitesimal steps, so that each step along the way, you haven't really thrown the system out of equilibrium that much, okay? And if you carry out the process really, really slowly in tiny steps, you're always pretty much in internal equilibrium. And that's good, because if your system is in internal equilibrium, it's going to have a pressure, just a single uniform pressure everywhere, volume, the number of particles, and the temperature also is just going to be some uniform value throughout. And it's much easier to talk about a system where there's just a single pressure, a single temperature everywhere, rather than those things varying at different places. So in Physics 47, we're only going to be considering quasi-static processes, okay? Now in the real world, not everything that happens is a quasi-static process. And in fact, this is a little bit of an idealization. But we use it because it makes the equations much more manageable to deal with, and it actually gives you some really good insight into the physics. So from here on out, any kind of process or any kind of change that we apply to a gas, we're going to assume it's quasi-static. Okay, so to clarify this idea of a quasi-static process, I'm going to sketch out an example. So let's consider a gas in a cylinder with a movable piston on the top. Okay, so this is the container, and let's say the piston is right over here, and that's what seals the gas into the cylinder. So our gas molecules are inside over here. So here's what I want you to imagine. Imagine that I move the piston up, so I can just sort of pull up on the piston, but I move it so fast that the gas doesn't have any time to respond. So we're going to move the piston up very fast. So what happens next is the piston is up here, but again, I've moved it so fast that the gas molecules don't even have enough time to expand into this new volume, so they're all still down here. So notice something. The system is not in internal equilibrium. And how do we know that? Well, here, look, if we think about the gas molecules down here, they have some pressure, but up here is basically a vacuum, so the pressure is zero. So we don't have the same uniform pressure and temperature, for that matter, everywhere within the container, so it's not in internal equilibrium, okay? So the process where I move the piston up really, really fast is not quasi-static,
But guess what? If I move the piston very slowly, the molecules have time to expand into the new volume at every step, and I'm always really close to internal equilibrium. So if I do it quasi-statically, which is very, very slowly, then we can always be in internal equilibrium. Okay, so the next thing we'll do is take a closer look at work. The variable W, which appears in the equation for the first law, is the work done by a gas. And what we want to do is come up with a formula for that. So what you should imagine is, let's say we have a cylinder, and there's a movable piston on the top of the cylinder. And let's just imagine there's no friction as the piston moves. And there's some gas inside of that piston down here. So we can change the volume just by the piston moving up or down. And what we'll find is the work done by this gas during a volume change, as long as it's quasi-static, is given by the formula W is equal to the integral of P dV. So P is pressure and V is volume. So we're integrating pressure with respect to volume. That's how you get the work. So I'm going to prove this for you in a second, but let's take a look at how we can use this result. So the graph at the bottom of the slide is called a PV diagram, where on the vertical axis, we have the absolute pressure, and on the horizontal axis, we have the volume of the gas. So we're plotting out P versus V. So if the volume changes, what's going to happen is you're going to move along this graph given by some kind of curve, which takes you from some kind of starting state to some kind of final state. And we know that the interpretation of an integral in terms of a graph like this is the integral is the area under the curve. So if we have a PV diagram like this, it's the area under the curve that gives us the work done by the gas. So in other words, this shaded area right here would give us the work done by the gas in this process that we're seeing plotted out on the graph. Okay, so let's see where the formula for work done by a gas actually comes from. So let's draw that cylinder where the piston is, let's say, up here, but it's been moved. So maybe it started off down here. So I'll draw it with a little dash line to show you where the piston started. Now, so the piston is moving upwards. We can say the distance that it's moved is dx. And while the piston is moving, the gas, which is in the cylinder down here, is exerting a force on it. It's pushing up on the piston. So let's just remember that work is a force acting over a distance. So let's just say force times distance, which gives us that the work done by the gas as the piston moves a little bit is equal to the force exerted by the gas times that little distance dx. And by the way, we're talking about infinitesimal quantities here. So dW gas is a tiny little bit of work and dx is a tiny little bit of distance moved. Now, let's bring in the notion of pressure, which is force divided by area, or P is F over A. Well, that means the force exerted by the gas on the piston is the pressure of that gas times the area of the piston. So in other words, this piston here has some kind of, the piston has some sort of area, and we'll call that A. All right, so therefore, the work done by the gas in this tiny little movement of the piston is the force, which is pressure times area times dx. Okay, well, the next thing we should think about is A times dx is the change in volume. We call this dV. So what do I mean by that? The volume of the gas has changed by some amount, and the volume that we've increased by, we we can think of it as a little cylindrical volume like this, where this is the area and dx is the distance we moved up. So that area times the height of that cylinder gives us the volume, which again is the increase in volume of the gas as the piston moves up. So therefore, we can write this as PdV. Now all we have to do is integrate both sides, and we'll get the total work done by the gas when we integrate it. And then we'll have on the other side of the equation the pressure times dV integrated like this. Okay, so that shows that the work done by the gas is the integral of pressure times dV. All right, so here is an example problem that I'd like you to try out and see if you can get the answer. In the PV diagram shown right here, we're seeing an ideal gas which expands. So it starts off over here where the volume is pretty low. The volume is 1.2 cubic meters, but then it moves along this curve and then it ends up at this final state where the volume is much greater. It's 6.1 cubic meters. So that's showing a gas expanding. And by the way, the pressure is dropping as the gas expands. So the question is, how many joules of work is done by the gas in this process? And then as a follow-up, how much work would we say the gas is doing in the reverse process if we went from here and then compressed the gas to a smaller volume ending up here? So see if you can work this out. Pause the video and then come back to it to see if we agree. Okay, so for this one, we're calculating work, and we know now that we can do this by integrating PdV. But probably for this one, it's easier to think of this integral as the area under the curve on the PV diagram. So let's calculate that area. First, we can notice that we have a little bit of triangular area right here. And then we also have rectangular area down here, and we need to include both of those to get the area under the graph. So for the triangular area, we have 1/2 base times height. The base is 6.1 meters cubed minus 1.2 meters cubed. That's, in other words, this distance right here. And the height would be this distance, which is 18.4 minus 4.5. And be careful, look on the axes. We have 10 to the 5 pascals. But remember, a pascal is a joule per cubic meter. And then let's add the rectangular area on the bottom, which is just going to be the base times the height. So the base is the same as before, 6.1 meters cubed minus 1.2 meters cubed. And then the height is now this right here, which is just 4.5 minus 0 times 10 to the 5 joules per cubic meter. So if you make this calculation, well, first of all, you'll notice that it comes out in joules because cubic meters cancel. And you should be getting about 5.6 times 10 to the 6, or 5.6 million joules. Okay, so that's just a little example as to how you calculate work done by a gas using a PV diagram. But let's consider the reverse process, where again, now the gas starts over here, and then it contracts rather than expanding, and ends up over here at this final state. So this will be our reverse process. And the way you should think about this is, well, here, let's start with the forward process, the one we just did. So the work done in the forward process, you can think of it as the integral from point 1 to point 2. So this will be point 1, the initial state. This will be point 2, the final state of PdV. In the reverse process, we're doing the same exact integral, except we're just switching, WR for reverse. Okay, so W in the reverse process, just switch the limits because we're starting at 0.2 and then we're ending up at 0.1 PDV. But remember, when you switch the limits of integration, that's the same as introducing a negative sign. So that would be the same as minus integral from 1 to 2 of PDV, which would just be minus the work in the forward process. So in other words, if you carry out a process like the expansion of the gas we showed here, the reverse process involves just the negative of that work. So if we're doing this in reverse, we have minus 5.6 10 to the 6 joules. Okay, and the meaning of that negative sign is, okay, if the gas is expanding, okay, the gas is doing work on its environment, so that's positive. When the gas is contracting, like in the reverse process, it's just the opposite. The environment is doing work on the gas to make that happen, right? Imagine you wanted to compress a gas to a smaller volume. You'd have to do some work. You'd have to push on it. And that's what that negative sign is telling you. Okay, so let's take a look at another example. In this one, we have a cylinder full of gas enclosed by a piston, but this time the piston is locked into place, so it can't move. It's not allowed to move. While this is happening, we add 1,000 joules of heat to the gas. So you can imagine maybe there's a little flame under the container. That's how the heat is added to the gas in the cylinder. So 2 questions. First one is, what is the work done by the gas? Is that going to be positive, negative, or 0? You don't need to put a number to it, just positive, negative, or 0. And second, what about the internal energy change of the gas? Is that going to be positive, negative, or 0? So try to work this out, see what you get. Pause the video and then come back to it once you have your answers. Okay. So to solve this problem, what we need to do is get a sense of what the process looks like on a PV diagram. Okay, so the process is we have a cylinder with some gas in it. There's a piston, but the piston can't actually move. So that means the volume of the gas in the piston is not going to change. So let's call that volume V0. And let's say this is where we start. This is the initial state before we start adding heat. If we start adding heat, we can imagine the pressure is going to have to go up. But again, the volume has to stay the same. So the final state is over here. It's a higher pressure, but it's the same volume. Okay? So the work done is given by the integral of PDV, which again we can understand as the area under the curve. But since the line going from the initial state to the final state just goes straight up, it's vertical, there is no area under that. Okay? Another way you can think about it is, there is no volume change happening. And whenever there's no volume change, we automatically know the work is equal to 0. Okay, so that was the first question, which was about work. There's no work being done by the gas. As long as the volume can't change, you don't have any work being done. Now, the second question had to do with internal energy. So for this, I want to take a look at the first law of thermodynamics applied to an ideal gas, which says Q is equal to W plus delta E internal. And in this case, Q was 1,000 joules, positive, meaning the gas is taking in that heat. Work is 0, and delta E internal, we'll leave it like that, but it's clearly something positive, right? So the internal energy of the gas is increasing, and what that means is the temperature of the gas is going up. That should be very intuitive. Of course, if we add some heat to the gas and we don't allow it to expand, it's going to have to increase its temperature. So the next thing we'll do is take a closer look at the variable Q. which denotes the heat transferred to the gas. Now remember, Q is one of the variables in the first law of thermodynamics equation, so we do need to know a little bit more about how to deal with it. And we've already seen this in the previous lecture. We talked about mass-specific heat. That's the amount of heat needed to change the temperature of 1 kilogram of the substance by 1 degree Celsius, or 1 Kelvin. It turns out in the Kelvin and Celsius scales, as long as we're talking about temperature changes, they're the same. But anyway, this gave us the equation Q is equal to m times C times delta T. And the units of C are joules per Kelvin kilogram or joules per degree Celsius kilogram. That's how we refer to the mass-specific heat. There's actually another way to do this. We can have a molar specific heat. So this is the amount of heat you would need to change the temperature of 1 mole of a substance by 1 degree Celsius or 1 Kelvin. So we're changing the way we refer to the amount of material. Instead of referring to a mass, 1 kilogram, we're referring to actually counting molecules, 1 mole. So this changes things a little bit. Remember N, this appears in the ideal gas law equation. N is the number of moles, okay? So we can write this as Q is equal to N times C times delta T. But now the units of C are joules per Kelvin mole. So instead of kilograms, we have moles as a way of measuring the amount of stuff. Or we could say joules per degree Celsius mole. Again, it's just a different way of counting the amount of substance. So for a gas, there's another complication because the value of C depends on exactly how we heat the gas up. So for example, if we add heat to a gas at constant volume, so we hold the volume constant, that's going to have a different value of C compared to if we add heat to a gas at constant pressure. We hold the pressure constant. So that's a little extra detail we're going to have to get into. But before that, let's do a sample calculation. So calculating a molar specific heat from a mass specific heat is essentially a unit conversion problem because again, we're converting from kilograms to moles. So for example, the mass specific heat of aluminum is 900 joules per Kelvin kilogram at room temperature. What is the corresponding molar specific heat in joules per Kelvin mole? So one thing that you're going to need to do this calculation is you're going to need the atomic mass of aluminum. It's 27 atomic mass units. So try to work this out and again, treat it like a unit conversion, going from units of joules per Kelvin kilogram to joules per Kelvin mole, and you should be able to work it out. So pause the video, see what you get, and then we'll go over it together. Okay, so the first thing that we'll note is that aluminum atoms have a mass, we call this the atomic mass, of 27 AMU. And remember, this automatically tells us that what we call the molar mass, okay, is 27 grams per mole. So if I have a mole of aluminum atoms, I know that the mass is 27 grams. That's what that's telling us. So now we'll do the unit conversion. We have 900 joules per kilogram Kelvin. So first, what I'm going to do is a unit conversion. 1 kilogram is equivalent to 1,000 grams. So we'll cancel those out. And then we also said that 27 grams of aluminum is what we have for every mole. So now we can cancel grams like this. And what we're left with is units of joules per Kelvin mole. That's exactly what we wanted. And if you calculate this, you're going to find it's 24.3 joules per Kelvin mole. So again, this is what we call our mass specific heat. Okay, that's 900 joules per Kelvin kilogram. And this is our molar specific heat. And that's how you convert from one to the other. So let's take a closer look at the molar specific heats. We know that for an ideal gas, the actual value of the specific heat depends on the process that's used to heat the gas. So it's not just a single constant anymore. It depends on how we heat the gas. In this class, we're going to look at two cases. The first one is heat transferred at constant volume. So this is what you should have in mind as far as heat transferred at constant volume. You can imagine you have a cylinder with some gas in it, and there's a piston, but the piston is locked into place, okay? And then we can add some heat, maybe put a flame to the outside of that cylinder, and some heat will be transferred to the gas, okay? So we want to know how the amount of heat transferred to the gas, that's Q, relates to the change in temperature, delta T, that will result from that. So the relationship is given by Q is equal to NCV delta T. So CV just refers to the fact that we're doing this at constant volume. Okay, we're not allowing the volume to change. On the other hand, we can imagine adding heat at constant pressure. So in this case, what you should be imagining is we have the same kind of gas in a cylinder with a piston, but this time the piston is free to move. There's nothing locking it into place. But what we're going to do is we're going to put a weight on top of the piston, and basically we can control the pressure of the gas by controlling the weight on top of the piston. So whatever's happening will control the amount of pressure with this weight. So let's say we add some heat, maybe again put the cylinder to a flame, and some heat will flow into the gas. What's going to happen is the gas will expand, so the piston will move up, okay? But also, in addition to expanding, the temperature will increase. So if we want to relate the amount of heat that we added to that temperature increase, we're going to use this equation. Q is equal to NCP delta T, where Cp is the specific heat for a constant pressure process. Okay, so those are the two types that we need to think about. Now, Cp is always going to be bigger than Cv, and I want to explain why. When you add heat at constant volume, again, there's no change in volume and there's no work being done. So all of the heat that you add goes into internal energy, goes to increasing the temperature of the gas. On the other hand, if you add heat at constant pressure, the piston can actually move. So the heat that you add is going to two places. Some of that heat is going to work, which moves the piston up, and another part of that heat is going to increasing the internal energy of the gas, increasing the temperature, okay? So because of that, you're gonna have, basically it takes more heat to increase the temperature at constant pressure than at constant volume. And that's why Cp is bigger than Cv. So, one thing I should mention is that up until this point, we don't have any formulas for Cv or Cp. We don't know how to calculate those things necessarily. That's something that's coming later in chapter 19. For now, I just want you to understand the difference between the two and why there's a different specific heat for a constant volume process versus a constant pressure process. And eventually, again, as we go further into the chapter, we will develop the formulas for those things and you'll know how to calculate them. So the next thing we'll do is go over some more terminology. It's really important to be able to understand the difference between a state and a process variable. So let's start with the state variables. A state variable is something that describes what a system looks like at a given moment in time. So in other words, a state variable does not depend on how the system got to its current state. It just has to do with what the current state is. So let's give some examples. Pressure, volume, temperature, the number of moles, internal energy. These are all things that you can just directly measure, so they don't depend on the history of the system and how it got to its current state. They're just things you can measure directly. On the other hand, process variables describe how a system transitions from one state to another. So it does depend on the process that the system is taking to get from one state to another. And so some examples of this would be things like work or heat. So the best way of distinguishing these two things, I think, is to think about a PV diagram, okay? If you're talking about a point on a PV diagram, you're talking about a state, because at a particular point, I know that my gas has a certain pressure, I know that it has a certain volume. And then from that, I could also use the ideal gas law, let's say, to calculate the temperature or anything else about the state of the system. However, if I'm thinking about a path between 2 points on the PV diagram, then I'm talking about a process, okay? So in other words, the gas is undergoing some kind of process to go from here to here, okay? And associated with that, we can calculate things like the work or the heat. But again, a process is not something about the current state of a system. It's about how you go from one state to another. And the last thing to say about that is we're always assuming quasi-static processes, so processes that are carried out very, very slowly. In fact, those are the only things you can really meaningfully plot out on a PV diagram. So let's sketch this out with a little bit of an example. So again, I want to sort of flesh out the difference between state and process a little bit more clearly. So let's go to a PV diagram. And let's say that this point will be our initial state. So our gas starts off with this pressure and volume, this point. And it ends up over here. So this will be the final state. Okay, now I can imagine drawing all kinds of different paths that take us from this initial state to this final state, but I'll just draw two of them. So let's say that's one of them. Let's call that number 1. And let's say this will be number 2. So again, just two different ways I can get from the same initial state to the same final state. So let's compare the two paths. Let's compare path 1 and 2. Okay, well, what do they have in common? What's the same between them? Well, same volume change, right? Because I start with the same volume and I end up with the same volume. So delta V is the same between the two states. Sorry, between the two curves. And delta P, right? That's the same for curve number 1 and curve number 2, because again, we start and end at the same pressure. And for that matter, same delta T, because by the ideal gas law, if I know volume and pressure, I automatically know temperature. And same with internal energy, right? These two, since we have the same temperature change, we have the same internal energy change. But what's different about the two? Well, what's different between these two curves that I've shown? Well, one is the work, right? Because work is area under curve on the PV diagram, that is. And of course, 1 and 2 have different areas under the curve. So there's a different amount of work being done in the two processes that are being shown here. Also, there's a different amount of heat, okay? So what's the same are the state variables, okay? So those don't depend on the path that we take, in other words. But what's different are the process variables. Those do depend on the path that we take, okay? So hopefully you see the difference between those two types of variables, and we'll end the lecture here, and we'll pick it up in the next video right where we left off. So until then, take care. I'll see you in the next one.